Right, you warn me if somebody raises their hand. Now I can just go like this and show everything. Okay, now you can hear me?
Yeah, I can hear you. The best thing to do would be to wait till the end of class and just check the little checkbox.
Which one are you seeing? You're seeing that one. That's not the one I want you to see. How can I, in Blackboard, how can I switch it to share that screen instead of this one?
It's not Blackboard, it's the same on your laptop. So we have to switch the mirroring function.
No, it is Blackboard. Let's go back to duplicate. Come on. Keep. Okay. Yeah, Blackboard.
So this is what they're seeing now.
That is what they're seeing now?
So this gray, it looks like you're good to go.
Okay. Except that we're in the wrong spot. Come on, where's my my cursor is missing. It started it in the wrong spot. Okay. Okay. Sorry about that, novice here. So Travis, they can still hear me. Is that correct? All right. Good. All right. So my name is Dr. Tarbox, Lawrence Tarbox, and Meredith is off traveling, and so she asked me to take this series of lectures. Actually, I was going to do them later in the year, but since she's traveling, she asked me to start early. So most of this material is probably going to be familiar to many of you. How many of you have a background in computer science? Yeah, so if you have a background in computer science, please try not to snore too loudly while we go through these slides, okay? The rest of you, please pay attention. You may or may not learn anything new. This particular information, it is from the Short-Lived and Camino book, chapter 5, and if we have time, it'll delve a little bit into chapter 6. I don't think the chapter 6 material, I'm not positive if that's going to be on any of your exams, so we'll have to clear that with Meredith. So when we get, I'll identify what that material is so that you can learn something from it, and then we'll find out from Meredith whether she's going to test you on it or not. Okay. A lot of this came from the topic outline from the clinical informatics subspecialty board examination. The outline for what topics do you need to know if you want to do a clinical subspecialty in medical informatics. And that's the level that they need to know. It is approximately the same level that is in the introduction to the book, the Blue Bible that Meredith carries around with her. All right, so so even if you know this stuff, this at least lets you know approximately what level of detail do you need if you were ever to take one of those board exams. Okay, so that's the importance of paying attention today, is just so you know what might get, what if you ever went for a certification exam, what might they hit. We're going to start off with talking about computer programming and software development methods. And if we have time, we're going to delve into a little bit into networking. So most of you are probably already familiar that a computer is nothing but a bunch of switches. So you can think of the switches as being on or off, or true or false, or a 0 or 1, but it's all based in what's called binary representation, which is, if you know, when I was a young wee lad, I used to go to these summer schools, and one of my favorite things to play around with in summer schools, they start teaching us about different number bases, you know, base 2, base 4, base 8, base 7. You can base a number system on any base. The one that we are familiar with is the decimal base, or base 10. If we were living back in some of the early ages of civilization in the Persia area, well, not Persia, excuse me, in the Iraq area, the number base they used there was 12. They used base 12. If you ever wondered where we got a dozen eggs, that's where it came from. And you know, I always was curious, well, why 12? Well, it's because of the bones on your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's how you counted. Whereas, you know, the rest of us, we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we were using the digits of our finger. That's why I call it digital. But computers, since they don't have fingers or bones, they only have switches, and switches can either be on or off. And so that's why the number system is base 2. And it's fairly easy to convert from one number system to another. So when you hear the term bit, what they're talking about is the state of one switch, either on or off, true, false, 0 or 1. If you take 8 of those switches in a row, that forms a byte. Now, why a byte? Again, it was just somebody's choice. I mean, some of the early computers, a byte was 6 bits instead of 8 bits. Probably they came from Iraq. I don't know. So an 8-bit binary number is called a byte. Hexadecimal, you may have heard that term before. Hexadecimal is just a convenient way to represent a binary number. Hexadecimal is actually base 16. It's a representation of a base 16 number. When we need to represent now numbers, you know, that's pretty obvious. If I'm trying to represent an integer number, I can very easily take a byte. I can represent numbers from 0 to 255 using 8 bits. Okay, but what about things like text? How do you deal with that? They're almost always done with some form of a coding system. So either the ISO 8859-1 or ASCII or ISO Latin, those things are represented as a single byte. The more common character coding system used these days is something called Unicode. And the most common representation of Unicode represents characters as 16-bit. In other words, 2 bytes put together. So to give you an example, if we had the text, in this case ASCII, of informatics, if I were to show you what that looked like in hexadecimal, you'd have that 69, 60, each one of those 2-character hexadecimal numbers represents a byte. Or if we were to put it in as a binary number, you'll see this big long 0, 1, 1, 1, 0, 0, 1. You can understand why people tend to like to use the hexadecimal when they're trying to represent, because it's a lot shorter than that big long binary number. So here's the first trivia question, probably the only trivia question for now. But can anyone tell me who George Boole was? Anyone know who George Boole was? He was from the 1800s. So maybe those who are in computer science have heard of Boolean algebra. Well, it was named after a guy named George Boole, who lived from 1815 to 1864. Obviously, computers didn't exist back then. But the notion of number bases did, and the notion of on, off, true, false, that sort of logic, that that base of how that all worked happened way back in the late 1700s into the 1800s. Boolean algebra was a way to describe a base 2, these binary interactions, these true relationships between true and false. And that's where that became the basis of almost all modern computers. They're all based on Boolean algebra. And they're all based primarily on these 4 functions, either a conjunction, a disjunction, a negation, or what's called an exclusive OR. And there are different ways you can represent that. You can represent it symbolically, as you see down here. What most people, I'm a visual person, so I like the diagrams. So a conjunction of X and Y means the things that is common to both X and Y. A disjunction means it can be in either X or Y. So it's the entire set of things that are either X or Y. A negation is things that are not. So if X is what we're interested in, the negation is everything that is not X. Exclusive OR is the one that some people have a hard time understanding. Exclusive OR, it's things that are either X or Y, but not both. Okay? And another way to represent these is that they use these symbolic representations of an AND gate, an OR gate, an exclusive OR gate, NAND, NOR, an exclusive NOR. The NAND just means a negated AND gate. So if this is an AND gate, this would be a negated AND gate. And you notice in the diagram the difference between the symbolic representation of an AND gate and an AND gate is just that little circle right there. So when you see a little circle on a diagram, on a logic diagram like this, that means take whatever that is and flip it the other way. So if the NAND gate came out with a true, then that little circle would turn it into a false. Okay, so another way to understand how these functions are what are called truth tables. So if I have my 2 inputs A and B, and if they're both 0, whoops, back. If they're both 0, then the output is 0. In the truth table for an AND gate, both of them have to be 1 before the output goes to 1. Okay, for an OR gate, if either one of them is 1, the output is 1. And for an exclusive OR gate, one or the other can be 1, but if they're both 1, it goes back to 0. So you might ask, well, what is this useful for? Let's take a simple combination of these circuits and what's called a half adder. So I have my 2 inputs, A and B. I have an exclusive OR gate that they're both feeding, and I have an AND gate that they're both feeding. And so if I do the truth table here, here's my input A, my input B. The output of the AND gate will be 1 if they're both 1. The output of the sum gate is the exclusive OR. It's only 1 if one or the other is 1, but not otherwise. And the sum gate, and so if you're doing an actual addition here, mathematics, if I take 1 plus 1, I'm going to get 1, 0 in a binary representation, because it's just like if I were to take 5 plus 5 in a decimal representation, they sum up to 10, and the one part of the 10 carries over to the tens column, right? So in this binary calculation, the same thing happens, but that carry happens very quickly because, well, you only have two digits that you can deal with, either 0 or 1. It's either on or off, it's true, false, whatever. So if you have 2 things that are true, it's going to create a carry, just like it would in addition. And that carry goes to the next half adder. This is just to give you a flavor of the sorts of things that the engineers do at the very lowest basic levels. And the idea, I think the reason why, so the question in my mind always was, well, why would they put this in a prep course for doctors? So why do you think it's important that you would understand Boolean algebra? To understand logic, right? Because even though we're talking here at a very low level, how to add one binary digit, for example, in this example here, the notions behind the Boolean algebra can be extended to any level of logic, and it's partly to get your mind thinking in a different way than what you're used to thinking. So I see puzzled looks. Well, that's because most people have a hard time thinking in binary, okay? It's like anything, it just takes practice. And so I wouldn't stress too much over it, but it's something that you'll need to learn how to do. And I think Meredith was going to give you a lab exercise specifically, because that seemed to be, when we were doing the prep course, the thing that folks struggled with the most was Boolean algebra and how that works. So believe there will be a lab exercise that will help you learn the Boolean algebra. I haven't got that prepped because she only gave me 2 days notice for this course. So we'll try to get that lab exercise to you as soon as possible, okay? And if you have any troubles, just come talk to me and we'll help you figure it out. Because sometimes it's one of those things that, at first it's very confusing, but after a while, all of a sudden the light goes on and you say, oh, that's what it's all about. So the idea is you take these little switches and those half adders and you can put them together into integrated circuits. So into switching circuits. So the very first computers were actually mechanical. They were made out of relays, which are electromagnetically operated switches. And they were extremely huge, extremely power hungry, and not terribly reliable because they were fully mechanical. So the story goes that one of the pioneers in computer science, she was a naval officer, her name was Grace Hopper, that the ENIAC computer was behaving badly. And so they were trying to figure out what was wrong. They were going through all the circuits, checking all the connections, trying to figure out what was bad. And she finally found in one of the relays, in the switch contact, there was a dead moth, little bug. She grabbed a pair of tweezers, pulled the bug out, and that's where the term "I have just debugged the computer" came from, because she actually pulled an actual physical bug out of the relay contact. And if you don't believe me, if you go to the Smithsonian Institute, you can see in one of the displays the actual moth that she pulled out of the relay contact. So that's where debugging a computer came from, because they actually had to pull this bug out of a switch. Now, vacuum tubes are another form of switch. So the next generation of computers were using a lot of vacuum tubes. If you guys are all too young to remember vacuum tube televisions and how, every year or so it would stop working and you'd have to call a guy in to replace the vacuum tube. Now imagine a system where you have thousands of these vacuum tubes, and how often are they going to burn out? So these computers, they replace a tube, they'd run for a few hours and then another tube would burn out. So they weren't terribly practical. The biggest advance in computers is when they discovered how to use transistors, a piece of silicon that's appropriately chemically treated, in order to then make it act as a switch. So now they could build switches that had no moving parts and no filaments to burn out. And that was used to make logic gates, similar to these adders that we were talking about. And so they would start putting together circuitry based on these logic gates in order to make a computer do something for them. The next big advance is something called integrated circuits. And the idea there was, well, instead of just having a single switch on a piece of silicon, what if we were to etch in multiple switches? And the count of those switches on silicon has been going up and up and up and up. So, for example, the first integrated circuit, I believe, only had a handful of transistors on it. The smartphone that you're carrying with you probably has on the order of 100 million transistors, and it's all on one or two of these integrated circuits. Each transistor on the newest integrated circuit, this is a little bit out of date. It says 22 nanometers wide. They're now down to 14 nanometers, and in some cases 12 nanometers for the width of the switch. So it's smaller than a strand of your hair. And there are newer tricks they're doing to try to pack more and more transistors onto one of these silicon chips, such instead of just having it in one layer, starting to stack them in 3 dimensions. So Moore, who was one of the founders of Intel, came up with this notion that the number of transistors that you could fit on one of these integrated circuits would double every 2 years. So the first integrated circuits that had, maybe only a dozen or so of these transistors were up to several hundred million. And that's because every year since 1971, his prediction that the number of transistors on a chip would double has panned out. Now, some people mistakenly think that Moore's law says that the speed of a computer doubles every 2 years. And that's not what Moore said. He said the number of transistors on a chip doubles every 2 years. But there's a correlation, obviously. The more transistors you have, the faster your computer can be. So, and the speed of a computer is typically measured in floating point operations per second. Since they're really fast these days, they're now up to gigaflops and even teraflops, and in some cases petaflops. So a gigaflop is 1 billion operations per second. And the cost of 1 gigaflop of computing power has been dropping dramatically over the years. So back in 1961, it cost 1.1 trillion in 1961 dollars, which in today's in 2013 dollars, that would have been 8.3 trillion dollars to get 1 gigaflops worth of operations, and it would be 17 million of the IBM 1620 units. 1620 was the fastest computer of the day. You would need 16 million of them to get 1 gigaflop. In 1984, we're down to 33 million, something a little more reasonable. In one of the second generation Cray. Cray was the big supercomputer manufacturer in the late 70s, early 80s. By 1997, you could do two of these 16 computer Beowulf clusters for about $42,000 and get a gigaflop. And as you go down, let's look at in June of 2013, PlayStation 4 came out. It cost 22 cents a gigaflop. Okay, and in January 2015, a basic stupid little home computer, not even an expensive one, this is a pretty cheap one, we're down to 6 cents per gigaflop. So the price of computing has plummeted dramatically. So why would that be of interest to us? The fact that the cost of computing is going down. Well, the more computing power you have, the more complex programs or computations one can do. So You know, when I was a kid, if the weather forecasters got the next day right, you were lucky, right? And now they can forecast out typically at least 4 or 5 days and often up to 14 days, and they're pretty accurate. And why? Because they have these monster supercomputers running mathematical models of weather patterns to help them predict the weather. Without those computers, obviously the better observations and the like also come into play. So how does that bode for biomedical informatics? You know, some of you are, well, when it's running, are using our supercomputer, and it's a little tiny thing. Could you do what you do, for example, with your sequencing, if you had to do it by hand?
Like maybe 1,000 years, I guess.
1,000 years? Yeah, even if you could use your Mac laptop, it would still take,
Like 100 years, I guess.
yeah, it would take forever. So by making the compute power cheaper and cheaper, there's more and more that people can do. So in bioinformatics today with the genome sequencing could not live without cheap, low-cost computing power. And my prediction, and it's getting to be that way, is that all of biomedical informatics, that even clinical operations of the hospital, they'd be, well, maybe you've heard when they holler code purple. Does anyone remember do you know what cold purple means? The computers are down, right? And everybody grumbles because they have to go to paper, and then you have to put it back into the computer when it's all over. So everyone's very highly dependent on computers. But I believe that in the futures we're going to be so dependent on it for routine diagnosis that that we have to have them. So having the costs go down is important. So this is the classic architecture of a computer. It's what they call the von Neumann architecture. So if you hear von Neumann architecture, this is what they're talking about, where you have something that's generating data that's being fed into the computer. The computer consists of a central processing unit, which inside the central processing unit, there's a control unit, and there's an arithmetic logic unit, and it's writing things to and from a memory unit, and when it's figured something out, it sends it to the output device. So this is the classic von Neumann architecture. Almost all computers today still follow the von Neumann architecture. The biggest difference is that we might network these things together, or we might have more than one central processing unit running against that memory unit. So the numbers of things, but the basic idea is still the same. You have the goes into, you have the goes out of, and you have the thing that churns away on the data in the middle. That thing in the middle, the central processing unit, there are two flavors that we typically encounter in the world today. One is called a RISC, and one is called a CISC, and that stands for Reduced Instruction Set Computer, or a Complex Instruction Set Computer. And the difference between the two, well, just as the names imply, is the nature of the instruction set. What the instruction set are the set of how you control that central processing unit, the arithmetic line. Tell the control unit what to do to the arithmetic unit and the memory to be able to get something done. You may have heard, whenever you go off and you buy a computer, they talk about, well, it's so many gigahertz, or it's a 1.3 gigahertz or 1.6 gigahertz. Well, that has to do with the how often can it execute an instruction. So a thought exercise: if I have a complex instruction set computer for one cycle, since it can do more than one thing in a cycle, if I have a 1 gigahertz complex instruction set computer versus a 1 gigahertz reduced instruction set computer, typically the complex instruction set computer is going to beat it out because it can do more things in one cycle. But the downside is the chip to make a complex instruction set computer can be very, very complicated. So there's been a battle brewing for years about, well, which is the better architecture? Should I put it all into the chip, all the complexity into the chip, or should I make the chip really simple, a whole bunch of them? So to give you a better example, if I'm trying to multiply two numbers, a complex instruction set computer typically could do that in a single instruction. So I multiply, it tells me where it's coming from, where the two numbers are coming from, and where they're going. On a reduced instruction set computer, it's going to take more steps. It has to first load one number, it has to load the second number, it then has to multiply it, and then it has to store the answer away. So these 4 steps are subsumed in this single step in a complex instruction set computer. So the advantage of the reduced instruction set computer is, so one of the disadvantages, their programs are longer. They take up more space. However, the instruction words are smaller because there are fewer operations that can be done in each instruction word. So in order to get the thing to run efficiently requires more work by the compiler, the thing that translates the code, your descriptions of what you want done into the code that actually does it. Those compilers get much more complicated with the reduced instruction set computer. But since they're small, they're cheaper to build, and they can you can put in performance enhancements that you can't do necessarily on a complex instructions set computer. However, the boundary between these two have been blurring over the years because they keep borrowing ideas from each other. So RISC processors, the instruction sets are getting more complicated as time goes on. The complex instruction set computers are introducing parallelism and pipelining, which used to be the venue of reduced instruction set computer. So where are these things used? Typically, low-end mobile systems like your phone will use a reduced instruction set computer. And usually the more complex machines, like your laptop, are using a complex instruction set computer. But there's a lot of blurring in between. Some of the fastest computers in the world are using, for example, the IBM Power chip, which is considered by most people to be a reduced instruction set computer. Watson, you've probably heard of Watson, the one that beat the Jeopardy champion, is built from Power chips. And those Power chips are all reduced instruction set computers. So how do you program these? So you've got these logic gates that are put into these integrated circuits. How do you make them do what you want to do? And that's where we deal with programming languages. And programming languages, you can program at different levels. So at the lowest level, you have what's called machine code, which is literally the bits put together into bytes that tell the machine what to do. It's ones and zeros. It's essentially, do any of you remember the, the paper tapes or the punch cards? That's probably also way before your time. Because that's the way they used to program computers, is they'd have these punch cards that have these little holes in them. And that told the machine what to do. That's the level of machine code that we're referring to. It's just a series of binary numbers. The machine knows what they are, but most humans can't read it. So most humans use something called assembly language when they're programming at that level, which uses short little phrases to represent what those binary numbers are. So, okay. It's still very tedious to use. So an example, this move, AL is a register, 6H1 is a memory location, so it's telling it to move the contents of that register into the memory location. If you have to do things at that level of detail, it gets very, very tedious. So most people use what are called high-level programming languages. That person who was the first to debug a computer, Grace Hopper, she was also one of the first people to create a high-level computing language. So for a high-level computing language, you're using English-like phrases or math equations to tell the computer what you want done. And usually, now you understand it, but the computer doesn't. So you need an intermediary that takes those English-like phrases or the math equations and converts them into the bits and bytes that the computer needs in order to actually run the program. So, and that process of going from the English down to the bits and bytes is called compilation. So examples of a complex language would be C or C++ or Java or Visual Basic. Those are high-level computing languages. Now coming to fray are things known as fourth-generation languages, which essentially abstract it even further. They'll work with matrices or deal with complex tasks like report generation, or even the database languages that you guys probably learned about a few weeks ago. Mathematica, MATLAB, R, many of you will probably encounter R in your life, or SPSS, which is the R for rich people. Sorry, I had to get my digs in. So that's what a high-level programming language is. There are also different programming languages, and somebody asked me, well, which is the best programming language? Well, the answer is, well, it depends on what you want to do, because different programming languages have their own strengths and weaknesses. So there are different styles of programming, some that affect how easy a program is to maintain, its memory and processor requirements. Typically, the more complex the programming language is, the more difficult it is to optimize the program to make the best use of memory and processor. So two of the most popular programming paradigms these days are one's called imperative or procedural, and the other one is called object-oriented. So an imperative or procedural language, Fortran, Basic, Pascal, C, these are imperative or procedural languages. They are just a set of tasks and say, do this, then do that, then do this, then do that. It's like a recipe. You have a list of ingredients, your data. You have a sequence of steps, what you're supposed to do with the data, with your ingredients. And then a set of common tasks. So in a recipe, it would say, whip the egg whites, or separate the eggs into yolks and whites, whip the egg whites, and so on. So you have these procedures for tasks. And these procedures and tasks can be reused throughout the program. And you can make more complicated procedures by combining smaller procedures. So that's an imperative language. An example, again, harking back to the days before you were born, is Apple Basic. This was used on the Apple II, the very first Apple that ever existed. And so take a look at that and see if you can figure out what the program is saying here. So it says for t, so t is a variable, just like in algebra. So t is going to move from 1 to 10. Whoops, let me get back here. T is going to go from values 1 to 10. And for each value, it's going to turn on the high resolution graphics. And then now another loop for a variable named n. It's going to go from 1 to 100. And then it's going to make this computation to get x, y, and c. And that c is then going to become the color, which then gets plotted out onto the screen. So if you were to watch this program running, unfortunately I don't have a movie of it, you would start with a black screen. You would see these lines just start radiating out from the center of the screen, kind of like you're, flying through, Star Wars or Star Trek, Starfield. It would do that, and then it would go blank and start over again, and just keep doing that over and over again. So that's a procedural program. It's a recipe for doing something. Object-oriented programs take that to another level. Some examples of object-oriented programs include C++ or Java, Objective-C, Swift, Visual Basic.NET. These are object-oriented. And the idea is that objects are data along with the procedures for manipulating that data encapsulated into a single unit. So programs then interact with the objects. Objects have different, can have different functions or characteristics or states, and a class is a blueprint for creating an object. Okay, so it describes for this particular class, this is the kind of data that the class holds. Here are the kinds of functions that you can do with the data. So an example of a class would be the class of all dogs. And an instance of a specific class is akin to, for example, a beagle is an instance of a dog. So, some terminology. If you ever have to talk to your programmers, they'll start spouting off all sorts of weird words. Objects typically have attributes. You can think of those as adjectives, things that describe the object. And methods. You can think of those as verbs, things you can do to the object. So, for example, a dog can have a fur color, could have a name, could have a breed. Those are the adjectives. But bark, roll over, those are verbs, things the dog can do. All right. An instantiation creates a new class member, setting the initial parameters for attributes and methods. The class encapsulates the attributes and methods. It says if they are whether or not they're kept hidden or whether or not they can be accessed by other objects. And composition allows complex objects to be built from smaller objects. So for example, a line class could be, we're talking in geometry here, a geometric line might have inside of it 2 point objects to describe 2 points in space. Inheritance is what allows a class to extend the structure and functionality of its parent. So, for example, if you had the manager and a staff, a class named manager and a class named staff, those both might have inherited things from a more generic employee class. An employee might have inherited from a more generic person class, for example. Objects can override their parents' attributes and mechanisms and methods through what's called polymorphism. So, for example, an animal class may have a verb, a method, that says make noise. And various subclasses, things that inherit from that parent animal class, such as dog, cat, or mouse, might implement make noise differently. That's what polymorphism is referring to. And classes typically have accessors and mutators, sometimes called setters and getters. So accessors, if I want to know, for example, the dog's color, I would use an accessor to get the dog's color. And I would use a mutator to set the dog's color. So here's in Java a fairly simple example of an object-oriented class. So we have this public class dog that extends a more generic class mammal. So that is an example of what? So let's go back. Is that an attribute method, an instantiation, an encapsulation, a composition, an inheritance, polymorphism, accessor, or mutator? So when I say dog extends mammal, what do you think that might be? Inheritance, exactly. That's inheritance. All right. So now we have these strings here, the name, fur color, breed, the noise. What are those? Those are the attributes, correct. And then we have set name, set fur color, set breed. Those are the setters. And get, those are the getters or the mutators. So these are the accessors, those are the mutators. And bark, it's a verb, okay? And the encapsulation comes from, for example, you see these all say private, whereas these other things say public. So these attributes, another class looking at this class can't see them. The only way it can get at those attributes is by using the accessors or mutators. And that's what's known as encapsulation. So it's hiding that from the outside world and giving them a better interface into it. Okay, so we went through that already. So the one thing we didn't talk about is polymorphism. If someone were to create a new subclass from dog, let's say beagle, then that dog's bark verb might produce a different sound than wolf. Okay? For example, if it were a Chihuahua, it might be yip instead of wolf. Okay? So how do I use that class? So if I have a program here, you start almost, in Java, you start with main. That's true of C++ and C, and I think most all of the more modern languages. You always have one routine that's labeled as the main routine. It's where you start. So my dog, I create a new dog. So that's called, what was that? Instantiation. Here I'm using the setters to set parameters for my dog, its name, its fur color. And here I'm using the getters. And here I'm making the dog do something. It's funny, I'm up here, you probably can't hear it, but I'm hearing something barking. So, all right. In these programs, you have things that are called control structures or event sequence. So you have primitives, which is, if you look at the program we just looked at, these would be the primitives here, where it's just setting values. You have choices and you have loops. Oops, going the wrong way, sorry. And then some of these, and then you also have what are known as variable types, and they just represent different classes of data. So you have primitive variable types, just the basic ones, such as Boolean, which would be a true or false. A character would be a letter. An integer, obviously an integer number. A float or double is a floating point number. In other words, a fractional number, a decimal number. You can have arrays of those primitive types. You can create composite structures by taking those primitive types and arranging them in complex patterns. And you can have types that represent specific things, like a date. In an object-oriented language, these things would typically be built by building new classes and subclasses and inheritance and polymorphism and that sort of thing. In a procedural languages, these have to be built into the language, essentially. Okay, we're going to talk briefly about types of data. Again, remember, this came from a review course, so this is more to tag your mind as to what sorts of things you need to be familiar with. So you might ask yourself, well, what if I don't recognize any of this? What should I do? that's where you might need to go back and review things. Get find a Coursera course or something like that to help learn what these concepts are. Depending on what you're doing, I think most of that will just come naturally because as you do, that's part of the reason why we have the project course, for example, because in some of your projects you have to be able to do these sorts of things. And that's the way we hope you would learn these concepts, is by doing, because it's not something that I can give you in a 1.5 hour lecture, obviously. So the types of data, there's categorical, meaning, and the best way to think of that is think of something with a name. They're usually mutually exclusive. They don't come in any particular order. Things like sex would be category, or male, female, or undetermined. Or mode is the only measure of central tendency of a categorical data. Ordinal, you would think of it does have a natural order. So categorical, there is no natural order, but in ordinal, there is a natural order. For example, small, medium, large. Both of these categories of data are what we call qualitative, because they describe something, but they don't give you any kind of numeric value for it. So for ordinal data, you can use median and mode. Quantitative data would be the two big categories there, interval and ratio. So an interval is something where each number represents a fixed distance of some quantity. So for example, in temperature, the distance between 32 and 33 is the same as between 77 and 76. So that would be an interval measure. And for an interval measure, you can do means, medians, and modes. And then ratios allow you to do comparisons. So area, distance, temperature, those are temperature in Kelvin as opposed to Fahrenheit. Those are ratios. And the reason why is because the definition of Kelvin, 300 degrees Kelvin, has twice as much heat content as 150 degree Kelvin. So that's a ratio, not an interval. Okay. And for a ratio, then you can add to all that list of stuff geometric mean. When you have data, you can then transform it. So for example, you can go from an interval to a ratio. For example, if I have the year diagnosed with cancer, that's an interval, right? I can convert that to years since the diagnosis of cancer. That's a ratio. Okay. Scaling an image, to make it bigger or smaller. So if I, for example, take every 2 by 2 clusters of pixels and average them together to create a single 1 by 1 pixel, that is going from an interval to an interval or ratio, and then down to a ratio. Interval to ordinal would be, for example, if I'm going to do binning to try to smooth the effects of observational errors. So, for example, if I take something continuous, such as age in years, and I break it up into categories such as neonate, infant, toddler, child, or adolescent, I've turned it into bins. That takes an interval and turns it into an ordinal. So it's something that was quantitative and turns it into something that is that is qualitative. So watch out when you do these conversions. You need to watch out for data loss, because transforming a data like that either cause data losses or gains. So the image compression we talked about, you're actually losing data when you do that. When you do binning, you potentially are also losing data. So can someone give me the time, please? It's 4:30? Okay. Does anyone need to take a break at this point? Otherwise, we'll just crash through the next section. So this next section is the part, and please don't all get up at once, but this is the part that might not be on your exam. I don't know. We need to check with Meredith. Okay, but this has to do with software development methodologies. This is in chapter 6 of the short-lived book. Okay. This is since many of us won't ever do programming, the whole idea of the first part was so you could talk to people who do programming and maybe potentially kind of understand them, right? This next part is the same thing. If you're going to direct a bunch of programmers, you need to be able to know what are they talking about when they're talking about good software engineering principles. And so that's what we're going to talk about for just a few minutes here, is about software development methodologies, or sometimes known as the software development life cycle. And software development life cycle is just like in any engineering where you try to apply a standardized approach in order to determine scope, organize tasks, figure out what do you need to test, and manage resources and time commitments to try to get a piece of software, and this actually could work for things other than software, that meets the customer's needs, that's predictable, and on a predictable and reproducible schedule. So that's the whole idea behind the software development methodologies. And basically, it's just as you might think, you come in phases. You're planning, you're implementing, you're testing, you're documenting, then you deploy it, and then you maintain it. So that's the software development life cycle. There are a couple of common models or methodologies that they use. The first one is called waterfall, where you do all of those things in sequence. You first do one, then the next, then the next, then the next, then the next. So you never move on to the next phase until the previous phase is done. And if you want to revisit a change that was made, you have to go through a formal change control process. You have to go back and then start the waterfall all over again. So it's very structured, but that also makes it very inflexible. But it's good for projects that have very stable requirements, where the requirements are not changing. It's a way to make sure that the requirements are met correctly. So the advantage is that you can find defects sooner when they're less costly to fix, but the disadvantage is that if you have a late-breaking requirement, it can be either really expensive or even prohibitive to fix because you have to go back to the top of the model. Because of that, most people don't use waterfall directly anymore. You will still find it in certain cases. Most of people have started to switch to one of the other two methodologies, which we're going to talk about. One is called spiral and one is called agile. And there's a lot of gray area in between. So spiral methodology is more risk-oriented. It tries to take the big project, break it into smaller pieces. Each piece is an area that has high risk and has related risks. So the advantage is that you try to tackle the high risk pieces first before you move on to the lower risk pieces, and then each of those pieces are then done with the traditional phases, where you determine the objectives, identify and resolve the risk, look at the alternatives, develop deliverables, and then plan for the next iteration. So sometimes this is called an iterative approach as well. So you start with the thing that's the highest risk. And when we talk about risk here, it isn't necessarily risk of hurting somebody. It could be risk that you're not going to get it done, right? So you take the piece that is the most important thing, either because it's critical or because it's the one that you're least sure about getting done, and you work on that first, and then you do the next one, and then you do the next one. So the final one is called agile, and this is one where you don't necessarily start out with a well-defined master plan, but rather you start focusing on very small steps and frequent loops and iterations. The idea is for Agile to work is you have to have your user community heavily involved, so that as you try to do things in very small steps. A typical step size would be 1 week or 2 weeks. So you do something really quick and then show it to the user community and say, is that what you had in mind? And they can tell you right away, nah. Go back to the next one. Is that what you had in mind? Well, they're getting closer, but you forgot about this and this. Okay, how about this? And so you just keep doing that. Very short steps, iterating, and as you go, you start building the thing to be bigger and bigger and bigger. So that's what's called Agile. Now, obviously, if you start doing to be like my grandkids when they try to build something in Play-Doh, right? And sometimes it ends up looking like a monstrosity, and the colors get all mixed up. So how do you prevent that? It takes a certain level of process management to make sure the thing doesn't, cascade into a never-ending loop. And some of the things that allow you to try to keep it focused down, one's called extreme programming. Extreme programming says that you always work in pairs, and you always have somebody double-checking your work. The other thing about extreme programming is the very first piece of code you write is the test. Okay? So you write the test, then you write the code. When the code passes the test, you're done with that particular step. System integration. This is the process, and this is where Agile has a really hard time, is in system integration, where Waterfall tends, because there's more planning involved. You can either do vertical integration, horizontal integration, or star integration. Each of them have their pluses and minuses, and I'm not going to go into great detail here. Vertical is you group subsystems by function into silos. So you integrate within a silo, but the silos don't talk to each other. Okay? Horizontal is the exact opposite. Every system talks to every other system through a bus. Okay? So this makes it really easy to replace individual systems, but it also means there could be contention on the bus, and they can't function as a whole, because all they're doing is spending their time waiting to talk to the other guy who's busy talking to some other guy who's busy talking to some other guy, and it gets so star is where you have unique connections between each element. It has high overhead, especially if the system is complex, but it's a way to avoid the bottlenecks on the bus. And again, there's no systems can use a mix of these different integration styles, but but if you talk about if you hear people talking about vertical integration, they're referring to here's a function and here's a function. Now it's possible that those two vertical functions might talk to each other over an enterprise bus. So there may be a bottom part of it that is horizontally integrated. None of this stuff works well without some sort of quality assurance and testing. And to give you a feel for how important it is, because the thing that I see all the time when people they go to their programmers and they're saying, I need this, 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 this. And he says, well, and they're not patient enough to wait for the testing. Even the programmers often, that little notion I mentioned with extreme programming where it said the first thing you write is the test, it's really hard to get developers to do that. Tests aren't fun, but they're extremely important, because the time to correct something that's wrong is lower in the early phases of a project than they are in the later phases of the project. So for example, if I detect an error during the requirements phase, before I've written anything yet, I'm just trying to get a feel for what it is the user wants. If I can fix it in that phase, that goes pretty quickly. But if I've gone all the way to it's released, it's in production, we said, oh crap, we're missing this very key feature. It may take a lot of work to get that feature put in once it's already gone out to production. So the idea behind quality assurance and testing is try to catch errors early on before they get to be too expensive. So, in a classic example that you will probably hear about why you need quality assurance testing is the Therac 25. This was a radiation therapy machine. It was built by a company up in Canada. The company actually had a pretty good reputation. They are now no longer in business. The machine was responsible for 6 accidents and 3 deaths from radiation overdose. Okay? And part of the problem was that they never really did full system testing until they installed the system. They shortcut the testing process. And what it was is they didn't do a proper risk analysis. What the machine actually had 2 modes of radiation. And one of the modes of radiation used a much higher beam current, but there was supposed to be this target, because the beam was supposed to hit the target, and then that created a different kind of radiation that went to treat the patient. That high beam current was not supposed to happen unless the target was in place. But they didn't have any kind of interlock that would prevent the high energy beam from coming out. And what they discovered in a post-mortem after they killed a few people was that there was a race condition, a seemingly innocuous piece of code in the GUI, something where they typed in a patient a name or something like that, that there was a race condition. It's completely unrelated to the code that dealt with the target, but for some reason that the race condition means that if this one hits first, one thing happens. If this one hits first, a different thing happens. And the problem was that the different thing that happened was that the target didn't move. And the only warning on the console is to say malfunction in a number, and it was not very well positioned. And of course didn't tell the user, danger, danger, things are not quite right. Okay? Patients were complaining, but the personnel didn't believe them because they thought the machine was working just fine. But what was actually happening was that if that race condition happened every once in a while, the target would not be in position when they went into the high energy mode. And then the patient was hit with a high energy beam that caused significant damage to their tissues in places that wasn't supposed to cause damage. So that's why, a concrete example of why adequate planning for the testing needs to be in place. Okay, you can do static testing or dynamic testing. So static testing is when you're looking at the code itself. Dynamic testing is where you're applying test cases to the code, and people should be doing both. So for example, in the extreme programming methodology, you have the test cases ahead of time. That's the dynamic testing. You always program in pairs. That's part of the static testing. And then finally, in extreme programming, you always, depending on the level of risk of the software, go through what's called a code review, where another team of programmers looks at the code and decide, and you try to explain it to them, and they decide whether you did it right or wrong. So that's static testing, those code reviews. Testing can be either white box or black box. So a white box test is testing the inner workings of a program, what's going on inside, and you're fully aware of how the program is put together. So code coverage analysis is one example of white box testing. This is where you instrument the code, you run the code through its paces while you're watching the code, and you see, did this line get executed? So you know that your tests covered every bit of code because you know whether or not all the lines are executed. That's white box testing, because you can see inside the program, you know how it's working. Black box testing is from the user viewpoint. You have no idea what's inside that box. You're just checking to see if it works correctly. So, for example, if a user enters an order, does it appear in the EHR? That's an example of a black box test. One of our best testers when I worked for Siemens was a guy that knew absolutely, he was not a radiation technologist, knew absolutely nothing about X-ray machines. He found more bugs than anybody else. Why? Well, because he would say, I wonder what would happen if I pressed this and this at the same time. I mean, he was just really good at just doing these weird, stupid things that you would think nobody in their right mind would do. That's not how this machine operates. But he would do it, and inevitably the machine would break. Well, that's the kind of breakage that caused the Therac 25 to kill 3 people. All right? That's why you need this kind of testing. You know, just really wild, off-the-cuff sorts of testing. So level of testing unit is usually a white box test done by the programmers. You have integration testing where you're trying to check, can my box talk with your box? That's typically also white box. It's still typically developer driven. System testing is where you put all the boxes together and trying to see if it actually matches the requirements. We said it was going to do this. Does it do it? That's typically black box. Acceptance testing is usually when you've turned it over to the customer and said, we've tested it, now you test it and see if it meets your requirements. That also typically is black box testing. And you probably will come across the term regression testing. And a lot of people are confused, I think, about what regression testing is. Regression testing is especially important in the agile methodologies where you're adding things incrementally to the function of the product. The question is, if I add something new, does it break something old? And so that's what you're testing in regression testing. Okay? So typically, this is why in extreme programming we say you write the test first, because then you put it into an integrated test build system so that every time somebody adds something new, it goes back and runs all the tests. So there's one team that I'm familiar with that, anytime anybody checked a new piece of code into the code repository, it would run the regression tests, which are all these unit and integration tests. Anything that can be automated, it would run those tests. And when it's done, if it passed, everything's good. It would turn on a green lava lamp. Okay? And so they were always watching for the lava lamp staying green. If somebody checked something in and it broke one of the tests, it would turn the green lava lamp off and turn on a red lava lamp. Now, if you're familiar with these lava lamps, they don't come on right away, right? So the team got used to trying to fix the problem, get it checked back in before the lava started bubbling up the lava lamp. So, you know, I got pretty good at it, but that's the kind of rigor, if you want solidly built software, that you need is to have the wherewithal to discipline yourself to write the tests, to make sure the tests are run, automate as many of them as possible. You know, usually when we were doing our project estimations, we would estimate anywhere from 1/3 to half of the development time was actually in writing and running tests. So if you're interested in some of this stuff, There's a list of additional readings. We'll post these slides up to the Blackboard, so you'll have them. And I think that's probably enough for today. We're at what? What time is it now? What?
10 minutes to 5.
Okay, so at this point, let's open up to questions. If you have any questions, anything you want to know about, anything that has to do with software or computer systems that you're always curious about, feel free to ask.
It was interesting that you put 2 semesters for the material in the one lecture.
Yeah, let's say this is like Computer Science 101 and 102 all rolled into one. So you just got, 2 major courses all rolled into one. But that's why I say this was done only at the level of understanding. The idea here was to get a grasp of the terminology, so that when you're talking to folks who are hardcore computer scientists, that you're not speaking English while they're speaking French. Well, if there's no other questions, I'll give you back 10 minutes of your day. But I would encourage, just for the fun of it, we'll try to get a lab exercise about the Boolean. I think that's what Meredith's intention was, but Boolean algebra, once you get the hang of it, it's pretty slick. I still wonder, though, how useful that is. So, is it really? Well, that's true. If you're trying to use one of the search engines in the library, it's helpful to know what all this Boolean algebra stuff is all about. All right. Thank you. Have a good day. So let's just stop sharing. Let's see if I can wind this thing down.